Welcome to the part 3 of 15th lecture in ML series. In this lecture, we will be discussing practical implementation of a perceptron. Let's quickly recap about perceptron. Perceptron is a single neuron model which can be used for a binary classification. It takes n inputs and classifies it as whether a positive class or a negative class. So the working of this perceptron is initially it takes input x1, x2, xn, and each input has some weights w1, w2, so on, wn, and you have a weighted sum after adding the bias w0. So whatever the weighted sum that will be given as an input to the activation function, here we are considering a step activation function. Whenever the weighted sum is greater than 0, it classifies it as a positive class, otherwise it classifies it as a negative class. Now for a given training data, finding these w0 to wn values is the learning problem. Now how it finds the w0 to wn for a given training data? That is, initially it starts with some random weights and then it adjusts the weights. And for adjusting the weights, it uses this training rule or a learning rule. So in every iteration, whenever the given data point is not correctly classified, then it adjusts the weights by using this. It finds an error, that is t minus y cap. Y cap is the output of the neuron and t is the expected output. So it finds that error, eta into error into the respective xi. That's how it adjusts the weights. So it will keep on adjusting weights until all data points correctly classified. Now we will see the implementation of this. So initially we are considering the perceptron class. So as we know that the perceptron has some number of inputs, so whenever we declare an object of a perceptron, we have to specify what is the number of inputs. So for the number of inputs, we have to create the respective weights. So the respective weights are, as we had w0 to wn, so we have created here the weights as n plus 1, where n is the number of inputs. Now how do you get the output of a perceptron? So output of a perceptron is, first we have to take the weighted sum, that is w0 x0 plus w1 x1 so on wn xn. So here x1 x2 so on xn are the actual inputs which are part of the inputs array, and we have to add an x0 equal to 1 as the first input. For that, what we are doing is we are inserting 1 into this inputs array at the 0th position, so that now we will be having an array first starting with x0, that is 1, followed by all other inputs x1 x2 so on x3 so on xn. So this is the input. Now we will be calculating the weighted sum. So simply we take a dot product with the weights that we have, and which gives me the weighted sum, that is sigma I is equal to 0 to n wi into xi. Now after that we have to apply a step activation function. As for the step activation function, if the weighted sum is greater than or equal to 0, we will say that it should return 1, otherwise it should return 0. So 1 is representing the positive class and 0 is representing the negative class. Okay. Now for a given training data, how it learns the weight values? So initially it starts with some random weights or 0 weights. So to check how it is learning, we are printing the values here, and we need to repeat until all data points correctly classified. That's why we have created here while 1, and then we are considering, so we are iterating through the each training example. So as we see here, the train function takes 3 arguments. The training inputs, that means each row of the training data except the class labels, and the class labels are there in the labels, and we have a learning rate eta. Okay, so the training input 0 contains that x1 x2 so on xn, and the label 0 contains what is the expected output. So to get the each training example as well as its label, we are going to use here GIF function, and whatever the inputs that we have, we will be giving it to this neuron, and we will find out the output with whatever the current weight values. With the current weight values, whatever the output that you get, now that output we have to compare with the label. So to compare, we are calculating here error. We are calculating it as label, that is t minus y cap. Y cap is the output of the neuron. So we calculate this error. Whenever error is not equal to 0, what it means is it is not correctly classified, because expected output is either 0 or 1, and the output that we are getting is also either 0 or 1. Whenever we have error equal to 0 means it has correctly classified. Whenever error is not equal to 0 means it has not correctly classified. Whenever it is not correctly classified, what we have to do is we have to adjust the weights. For adjusting the weights, we are using this wi equal to wi plus eta into error into respect to xi. So we are performing here a vector operation, so that all weights are adjusted at once, and whatever the weights that are after adjustment, that we are printing. And we are also calculating a total error, because once after completing all the training examples, if the total error is 0, that means all data points are correctly classified. To find out that, we are finding out the total error. Okay. Now when the total error is 0, means it is converged, that means all data points are correctly classified, then we will come out of the loop by using break. Okay. Now after that, we are printing the final weights. So this is how one can implement a single perceptron or a single neuron, which can be used for a binary classification. So the reason for using here a class for a perceptron is, later when we extend it for a multi-layer, it will be easy if you consider it as a single class. So let's run it. So if there are no errors, then you will get a green tick mark. So we got a green tick mark. Next. So now we will test that implementation by taking a boolean R function. So in the case of boolean R function, we have the training data, that is 0 0, 2 input boolean R. That is, it takes 0 0 0 1 1 0 1 1. For 0 0, it should give 0. For all the remaining inputs, it should give 1. Okay, and then now we have created a perceptron object. Whenever we create a perceptron object, we have to specify what is the number of inputs. Based on the number of inputs, it is going to create a weight array of length n plus 1, where n is the number of inputs. Now next, we have to train the model by giving this training data. So the training data, this is the input array, and then the labels, the respective labels, and we had here initially given the learning rate as 0.5. Now let us run this. So when you run it, so we had considered the initial weights as zeros. Or now when we give input 0 0, the expected output is 0. The output of the perceptron is 1. So we have an error -1. So the weights are adjusted, and after adjusting the weights, we got this. And then again we consider the second input 0 1. The expected output is 1, and the output of the perceptron is 0. So again we have error 1. So we will be adjusting the weights. Next, for 1 0, the output of the perceptron is 1, and the expected output is 1. The error is 0. So we don't need to adjust the weights. Whatever the weights that are there now are correctly classifying this data point 1 0. Next we have 1 1. Expected output is 1, and the output of the perceptron is also 1. We don't need to adjust the weights. Now again we have 0 0. The expected output is 0, but the output of the perceptron is 1. We got an error -1. So weights should be adjusted, and we got this. And similarly, when the input is 0 1, again you need to repeat this process. So that means it actually repeats this process. Whenever you have in any iteration all 4 data points like 0 0, 0 1, 1 0, 1 1, where you get an error 0. So when all data points are correctly classified, it reports the weight values. So these are the weight values. The final weight values that we got as minus 0.5, 0.5 and 0.5. For this, it correctly classifies the all the data points of the OR function. Suppose if we want to test AND, we can also just we need to change the output. For 0 0 the output is 0, for this the output is 0, for 0 1, for 1 0 the output is 0, for 1 1 it is 1. So when you run it, now we get a different weight values. These weight values are used for classifying the boolean AND function. This is how a perceptron finds these weight values. Now if you want to test, you can also test it. So whatever the weight values that we got now, we are giving it to this perceptron and then we are finding out the output, and then that output and the expected output we are comparing. So let's run this. So if you give 0 0, the expected output is 0 and the predicted output is 0, which is correct. So that means all data points are correctly classified. In whatever the example that we had considered so far, either it is a AND function or a OR function, both are linearly separable, as we had seen in the previous class. So if they are linearly separable, it is going to give the correct weight values. Suppose if it is not linearly separable, suppose we consider a case where it is not linearly separable. So if we consider an XR here, XR as you recall, for a even number of ones it is going to give 0, for odd number of ones it is going to give 1. So for 0 1 1, for 1 0 1, for 1 1 it is 0. So it is it is not linearly separable. So when it is not linearly separable, if you run it, if you run the perceptron algorithm, it is not going to converge. So it will run, it will keep on running. It will keep on running. So it will keep on running because it's not possible to draw a single line to separate those classes. So just to stop, we can click on this again, interrupt the execution. So thank you.